Hello everyone, welcome back to Statistics. So in the last lecture, we began discussing confidence intervals. Today we're going to continue on that same discussion. Let's review the main points from our last lecture. Overall, last time we just introduced confidence intervals. As an example, we used the story of Jonah P. Polster. She conducted a poll of 1,000 East Virginia voters and found that 53% planned to vote for Christina Green. So we can say P, the sample proportion, was equal to 0.53. The problem for Jonah and for all pollsters is that numbers from their polls contain sampling error, and therefore are unlikely to give an exact estimate of the true value in the whole population. When Jonah reports the results from her poll on, let's say, the evening news, she can say something like this: "My poll shows that 53% of voters plan to vote for Green, but the poll's margin of error is about 3%. What Jonah means is that she is 95% sure that the true value of pi, which is the proportion of voters in the state who plan to vote for Green, is somewhere between 50 and 56%. The way that statisticians state the same idea is that the 95% confidence interval of pi around p is 0.50 to 0.56. So this confidence interval is written like this, with 0.50 and 0.56 enclosed in parentheses and separated by a comma. So the number on the left, 0.50, is called the lower limit, where the number on the right is called the upper limit. Pollsters are interested in the confidence interval for pi around p. But to help you understand confidence intervals, during the last lecture, I focused on something a little bit different: the confidence interval for p around pi. I begin by showing how you can estimate a 95% confidence interval for p around pi just by looking at a histogram of the sampling distribution. To begin with, we know that the expected value of p is the mean of the sampling distribution, so it must be right here around the middle. And we can identify the value of p that is about 2 standard errors above the expected value, and we can also identify the value which is 2 standards below the expected value. We know in a normal distribution, 95% of our scores will lie within 2 standard deviations of the mean. So this is all based on the central limit theorem, and it guarantees that the sampling distribution of p is normal, and that the standard error is the standard deviation of the sampling distribution. That means that in the sampling distribution of p, 95% of samples will have a value of p within 2 standard errors of the expected value. So 95% of the samples are in the shaded rectangle. And to put it another way, 95% will fall within 2 standard errors of the expected value. Or even another way, 95% of these samples have a p that is between 0.52 and 0.58. So we draw the 95% confidence interval, which indicates that 95% of samples have values of p that fall within this interval. And we can write our conclusion as shown here. So 95% CI, so confidence interval for p, equals parentheses 0.52 comma 0.58. So this statement means what we saw on the histogram. 95% of samples have a p between 0.52 and 0.58. So here are some abbreviations that are commonly used. So instead of saying the lower limit of the 95% confidence interval equals 0.52, we can just say p lower equals 0.52. And likewise, instead of saying upper limit of the 95% confidence interval equals 0.58, we can say that p upper equals 0.58. So after I showed you how to estimate the confidence interval for p around pi by using your eye and your knowledge of a histogram of the sampling distribution, we showed you how to actually use the mathematical formulas to calculate the confidence interval. And the example, we used East Virginia again with 700 samples and 1,000 voters in each Okay, so if we want to find the 95% confidence interval for P, what we have to do first is find the expected value of P, the standard error of P, and we need to know N. We know that the expected value of P is equal to pi, and that's the true proportion in the population. In our example of East Virginia, it's 8 million. Do we know the exact value of pi? No one really knows it, except for the recording angel in charge of, knowing all these voting and opinion things. So we never exactly know the value of pi, because you would have to go and measure and take every person in that sample. And in East Virginia, it's 8 million. So that's pretty much impossible. So if you want to know pi, someone has to give it to you. So that'll be either the textbook or the recording angel. So once you know pi, you will be able to use it to calculate sigma. And sigma is just the standard deviation of the population. And you can see this formula is right here. And once you have sigma, you can use it to calculate the standard error of P using the formula on the right. Once you know the expected value, the standard error, and N, you can use the formula shown here to calculate the upper and lower limits of the confidence interval. The idea behind these formulas is very simple. You're just using these formulas to identify the point that is 2 standard errors above and 2 standard errors below the expected value. So the two formulas here will tell you that the upper limit of the confidence interval is 0.582 and the lower limit is 0.518. So you can see that parentheses 0.518 comma 0.582. So now that we've reviewed everything from the last lecture, let's talk about new material. So today's lecture will continue on the topic of confidence intervals. Before moving on to new material, it'll be helpful to review something that you guys already know about. That is the distinction that we make between sample statistics, population parameters, and sampling distribution characteristics. These are all related to the topic that we discussed earlier, and that's just the difference between the sample, population, and sampling distributions. So if we're talking about samples, we can use it to calculate the sample statistics. So if the variable of interest is a Bernoulli variable, we can talk about P. We can also calculate the mean of the sample and the standard deviation. There might be other numbers that we may want to calculate. For instance, we might calculate the variance, or the minimum value, or the maximum value. So if we're referring to samples, then any of these numbers are known as sample statistics. If we have a population, we can calculate similar numbers that are referred to as population parameters. For instance, for a Bernoulli variable, we might calculate pi, the proportion of individuals in the population who have a value of 1 on that variable. We can also calculate mu, which is the mean in the population, or sigma, which is the standard deviation of the population. Every population parameter, or almost every, has a twin sample statistic that corresponds to it. So, for instance, pi corresponds to P. They both measure the same thing, the proportion of individuals with a value of 1, but where pi measures it in the population, P measures it in the sample. Likewise, the sample mean and the population means are twins, and the sample standard deviation and the population standard deviation are twins. So statisticians usually use Greek letters to indicate population parameters and letters from the Latin alphabet to refer to as sample statistics. And this was just to save time, because if they didn't have these different ways of doing it, they would have to refer to, the mean of the sample or the mean of the population. So if you hear someone say, mu, you automatically know that the status is something from the population. Finally, there are sampling distribution characteristics. Two you are familiar with are the expected value of and the standard error of P. As you know, they are just the mean and the standard deviation of the sampling distribution, but they are given different names to help keep them straight from the population parameters and sample statistics. Here are two more sampling distribution characteristics that we haven't talked about yet, but we'll continue talking about them today in lecture. They are characteristics of the sampling distribution when we have mean. So the sampling distribution of the mean is constructed almost exactly the same way the sampling distribution of p is constructed. As we know, first you collect k samples of the individuals. Each sample has n individuals, and for each sample we can then calculate the mean. So let's say we have 700 samples. We would have 700 different Excel sheets with 700 different values of the mean. Then you would use those 700 different values to make a histogram, and that would be the sampling distribution of our mean. Then what we can do is calculate the average of these 700 values, and that would be the expected value of the mean. So you can see that right there, expected value x bar. Or we can also find the standard deviation of those 700 values, and that would just be called the standard error of the mean. During the last lecture, you learned how it's possible to start with the value of pi in the population and then identify likely values of p in the samples. So this is called finding the confidence interval for p around pi. So today what we're going to learn is how to start with the value of p in the sample and then identify the likely values of pi in the population. This is called finding the confidence interval for pi around p. Now, this confidence interval is what pollsters need. They have a sample with a particular value of p, and what they need is some way to figure out the value of pi because they are interested in the population. After all, finding pi is the goal. They don't really care about p in their sample except that it gives them information about the value of pi in the population. For instance, Jonah P. Polster has her sample of 1,000 randomly selected voters with 53% planning to vote for Green. She isn't particularly interested in how these 1,000 people plan to vote for her, except that she can learn something about the 8 million people that live in the whole state. And the confidence interval for pi around p answers her question. You can be 95% sure that pi is between 0.50 and 0.56. That is, in the state, at least half of the voters plan to vote for Green, and may be as high as 56%. The answer isn't as precise as we would like, but it's precise enough to be useful. So first, let's understand why the sampling distribution of pi around p works. We'll start with this histogram, which you have seen several times before. It is the sampling distribution for p, so the red dot in the middle is equal to the expected value. More importantly, it's equal to pi. Now, we happen to know what pi and the expected value are, and that's 55%. But we only know because of the recording angel. Jonah doesn't know. So the red line at the center of the graph is the confidence interval for p around pi. The confidence interval is centered on the expected value, and that is the dot that represents the expected value is the same distance from the right end of the confidence interval as it is from the left end. It is not what we are looking for. That is 55% of all East Virginia voters. If you measure the distance on the scale for p, the distance is approximately 0.58 minus 0.55, which is 0.03. However, there's another scale that we could use, not shown on the graph. So the right end of the interval is 2 standard errors from the expected value. And how about the lower limit? It's just 2 standard errors below. So we know that the left end of the individual is also 2 standard errors away from the expected value. And we know that the whole interval is centered around the expected value. So now let me stress this. The confidence interval of p around pi. It's not the confidence interval for pi around p, which is what we and all pollsters want. But this confidence interval will help us find the one that we want. So we're going to create a second confidence interval around p that is the same length of the confidence interval for p around pi. Here's the second confidence interval. It looks like a little yellow yardstick. I've temporarily placed it above the confidence interval for p around pi so you can see how the two confidence intervals are the same length. So let's take this confidence interval that we just created and we're going to move it around. It is the confidence interval around p, not pi. So let's make sure the second CI is centered on p. So first, we'll move it to the second CI. So it becomes a confidence interval around p. As you remember, Jonah had a sample of 0.53. So let's take that new CI and center it around 0.53. So now the upper limit of this new second CI, so the upper limit of the second CI is 2 standard errors above 0.53. The second CI is the same length of the CI of p around pi, so just remember that. So here's the lower limit of the CI. So how far is it from p? 2 standard errors. So the lower limit is also 2 standard errors from p, so 0.53. And here's an important question. Is pi within the second confidence interval that we created around p equals 0.53? This is a critical point because the confidence interval around p equals 0.53 lies between the left and right ends of our yardstick. Anything between the two ends of the yardstick is within the confidence interval. We can see that pi is between the two ends of the yardstick. So pi is within the confidence interval. But you can see that 0.55 is contained within that yardstick. We can center the second CI around 0.53 and use formulas to calculate the upper and lower limits of the confidence interval. So the upper limit is 0.53 plus 2 standard errors, and the lower limit is 0.53 minus 2 standard errors. So during the last lecture, we found that the standard error for this sampling distribution is 0.015. So we just plug in 0.015 for the standard error in the formula. And when we do the math, we get the lower limit as 0.50 and the upper limit as 0.56. We can see if pi falls within that confidence interval. So pi is 0.55. So does 0.55 fall between 0.50 and 0.56? It does. Okay, so let's try another value of p. So p equals 0.51. Very few samples in our sampling has p equals 0.51. So what we can do is we have that same confidence interval and let's center it around 0.51. Now you can see that, this confidence interval does not overlap with pi. Okay, so let's just use the formula again. The upper limit of the second confidence interval is 0.51 plus 2 times the standard error. The lower limit is 0.51 minus 2 times the standard error. And when we do the math, we get the confidence interval as being 0.48, comma 0.54. And as we notice, pi, which is 0.55, does not fall within that confidence interval. Okay, so let's move our second CI again. So let's center around 0.57. So the question here is pi inside the second confidence interval that is centered on 0.57? So as you can see, it overlaps. So it definitely is. Let's do the math again. So just 2 times standard error, and we can subtract it off or add it, just depending on if we want lower limit or upper limit. And as you can see, pi falls within our confidence interval. Let's try another value. So p equals 0.59. If we look at it here on the histogram, we have our portable confidence interval, and you can see, look, pi is not contained within that confidence interval. So there's a pattern here. For some values of p, we make a confidence interval around pi, and pi falls within that confidence interval. But for other values of p, we make a confidence interval around p, and pi does not fall within that inside that confidence interval. There's a simple rule that tells us whether pi will or will not fall within that confidence interval around p. And here's the pattern. When p is within the CI around pi, then pi is within the CI around p. Now I'm going to show you with some slides. The blue dot indicates p, and you can see the confidence interval around it with the yardstick, and then the red dot indicates pi, and the red line is the confidence interval around pi. At this point, pi, the red dot, is clearly not inside the confidence interval around p, so they do not overlap. But watch, I'm going to move the blue dot and its portable confidence interval towards pi. And I want you to tell me when the center is within the confidence interval. Okay, now you can see that these are overlapping. So the red dot, pi, is now within the confidence interval around p. And you can also notice that the blue dot, which represents p, is inside the confidence interval around pi, or the red line. So these things happen at the same time. When the red dot representing pi goes within the confidence interval around p, the same moment the blue dot representing p goes within the confidence interval around pi. So let's continue moving p even closer to pi. Okay, do you understand what I'm demonstrating here? So when p is within the confidence interval around pi, then pi is within the portable confidence interval around p. So how many samples in the sampling distribution have p within the 95% confidence interval around pi? So just to repeat the point of this little demonstration with the moving dot, when p is within the confidence interval around pi, then pi is within the confidence interval around p. So how many samples are within this? 95% of samples. If p is within the confidence interval around pi, then pi is within the confidence interval around p. So that must mean that for 95% of samples, pi is within the 95% confidence interval around p. So here's what we learned. If one was to randomly draw a sample and calculate p for it, and two, you draw a confidence interval around that p, then there is a 95% probability that pi will be located in the confidence interval around p. And this is what pollsters do. They randomly draw a sample and calculate p. They construct a confidence interval around p, and then they say that they are 95% confidence that pi is within that confidence interval. And that's right. For 95% of samples where they do this, pi will be in the confidence interval. So now that we have established the reasoning that underlines confidence interval for pi around p, let's talk about how it's calculated. When we are talking about the portable confidence interval around p, I gave you this example of how it would be calculated when p is 0.53. The upper limit of the confidence interval is 0.53 plus 2 standard errors, and the lower limit is 0.53 minus 2 standard errors. So here's the general formula for calculating the 95% confidence interval around p, and it's just to get this upper limit, add 2 standard errors to p, and to get the lower limit, subtract 2 standard errors from p. There is a complication. It's usually impossible to know what the standard error really is. You remember this formula for the standard error of p? To solve this formula, you need to know sigma, the standard deviation in the population. How do you know the standard deviation in the population? No one knows the standard deviation. For instance, so of course we do have the formula to calculate sigma. It's the square root of pi times q. But no one really knows pi. In fact, that's why pi's polls are done. We can't directly know what pi is, so we can try to gain information by asking and taking a sample. I suppose you could ask the recording angel, like the last lecture, but that's generally not an option. So statisticians have come up with a different approach. So this approach is substituting estimators for parameters. So that is when a parameter like pi or sigma is needed in a formula, but not available, other numbers called estimators are used in place of the parameters. For an instance, suppose we need pi. We don't know pi. Since there is usually no way for us to get the exact value, we use the estimator, pi hat. Pi hat is the estimator. Its symbol looks like pi, but with a little hat on it. Little hat means an estimate of, or a prediction of. And you may remember that from our lectures on regression. We had the predicted value of y as y hat. The value of the estimate is p. So the sample statistic is similar to pi. So when we have a formula that requires pi, we can just plug in p instead. Similarly, suppose we have a formula that needs mu, the population mean. The estimator is called the estimated value of mu, and it's just mu hat. So if we want to plug in a value that we do know, we can just use the sample mean. Again, if a formula calls for sigma, we can use the estimator called sigma hat. And guess what we can use? We know the formula for finding standard deviation, so we can just substitute it in there. We can substitute the estimators for these parameters. So we're using the sample collected by Jonah, and in that sample p is 0.53. So q is going to be 1 minus p, or 0.47. So here we have that. So we need to substitute our estimators. So p is going to be 0.53. Q is going to be 0.47. When we do the math, we get 0.499. So let's plug it into the formula. 0.499 divided by the sample size. So what was our sample size? 1,000. So we just plug in 1,000 right there. Then we do the math and we get 0.0158. So the standard error is equal to 0.0158. Now you may recall we actually know that the true standard error in the population is approximately 0.015. So the estimated value using the estimators is off, but only by 0.8 of 1,000. So that's actually pretty close. So now we can use standard error into the formulas for our confidence intervals. And when we do the math, we get the upper and lower limits. So lower limit of 0.498, upper limit of 0.562. Again, these results are not exactly the same as what we got in the last lecture. When we had the recording angel give us the true population values, it's a little different because those are the true values. But when we use in our estimates, they're very, very close. And statisticians have done a lot of research on this, and the clear conclusion is that substituting the sample statistics for the population parameters work very well and give us excellent estimates of the confidence intervals. So let's summarize how to calculate the confidence intervals for pi around p. When we have a sample of p, we calculate the 95% confidence interval around it using these formulas. We can use these formulas to calculate the standard error. We just have to substitute these estimators for the parameters. We then substitute the estimator values for the estimators, and the estimator values are simply the sample statistics for our sample. We end up substituting p in place of pi. In the examples, we have always been discussing p and pi. So let's use means. There are many other cases in which you collect a sample, calculate the sample mean, and then calculate a confidence interval around the sample mean to identify the most likely values of mu, the population mean. The underlying logic and computations are almost identical to the ones that we've already learned for p and pi. I'll show you an example using 100 bags of chocolate chip cookies from a certain manufacturer. We can count the cookies in each bag, and then we'll end up with a list of 100 numbers. Each number represents the number of cookies in a particular bag. So let's say we count the 100 bags of cookies, and the mean is 45 cookies, and our standard deviation is 5. They say there's an average of 50 cookies in each bag. So we want to test if this claim is true. And we can use our confidence intervals to do that. So in this example, we talk about individuals as a bag. So our sample consists of 100 bags of cookies. So our N is 100. And the population we're trying to learn about consists of all bags of chocolate chip cookies produced by this manufacturer. The variable in this problem is the number of cookies in each bag. The sample statistics is 45 is the mean of cookies in the bags, and then the standard deviation is 5. The population parameter you're interested in is mu, which is the average number of cookies in all bags that the manufacturer sells. So here's the general formula for the confidence interval for pi around p. So we want to calculate the 95% confidence interval for mu around the sample mean, and it's virtually the same. Let's just see how these formulas actually change. Instead of using p, we use x bar, and we use the standard error of the mean. So there's that problem again. No one really knows the standard error of the sample mean, but the solution is the same. And that solution is just the substitute estimators for our parameters. The formula for the standard error of the sample mean is the same as the standard error of p. The sample mean is simply substituted for the population mean. In our example, the standard deviation is 5, and the sample is our 100 bags of cookies. So what do we do when we do the math? So 5 divided by the square root of 100 is 0.5. So now we can just plug it into our formula. So our mean is 45 cookies, and we just add it to 2 times the standard error, or 2 minus the standard error. Let's put our standard error in. So we substitute 0.5 in there. And then when we do the math, we get our upper limit as being 46 and our lower limit as being 44. So this is how we would write our 95% confidence interval for mu when our mean cookies is 45. So parentheses 44, 46. In our question, we wanted to test the claim that the manufacturer says, that the average number of cookies in each bag is 50. So does 50 lie within our confidence interval? Considering the confidence interval you calculated based on the sample of 100 cookies, I'll leave it up to you to decide whether the manufacturer's claim is true. That concludes the lecture for today.